Thank you. So to connect with the invited lecture yesterday, I asked the question, your data is in the cloud. Do you know where your data is? So we have a lot of data in the cloud, email, file backups, financial information. Now, the data is visible to the server, which can encrypt it, but encrypt it with its own keys. So basically, anyone with access to the server has access to the data. Sorry. So why not encrypt it with your own keys, like having Gmail but encrypted under the user's keys? Mainly because we want to do some stuff with that data, like searching it. So the question is, can we keep the data encrypted and also search it? Or as the proverb says, can I eat the cake and have it too? So this motivates the problem of searchable symmetric encryption, in which an owner of data, which we call it a client, pre-processes the data, encrypts it, generates some indexes or whatever pre-processing, puts the processed data in the server, keeps a small state, like a cryptographic key, and later it sends encrypted queries to the server to be searched such that they give me all the emails where Alice is the recipient, not sent by Bob, containing some words. And the goal is that the server will return the encrypted matching documents, but without learning the plaintext query or the plaintext data. And since in this setting, the same person that writes the data also reads it, then we can use symmetric techniques, giving hope to have solutions that actually can work on real bulk data. And although this problem is quite natural relative to the problem and to the cloud hype, actually there is relatively little is known in the area. So of course we have generic solutions. One of it is send all the data back to the client, and the client will search. That's a lot of communication. On the other extreme, you can use fully homomorphic encryption, and you don't have too much communication, but of course, that would be impractical, at least today, with what we know about fully homomorphic encryption. A less impractical solution is using oblivious RAM, which actually is becoming more and more practical with the latest works, but still, at least today, wouldn't be able to really manage a big database. So what is known about dedicated solutions, essentially for single keyword, then we know a lot. A single keyword means that you give only one keyword, search all the email with the word crypto, or all the records with the name Bob. And the server is allowed to learn the set of encrypted matching documents, but not the keyword or the plaintext data. And in that setting, there are quite a few works that achieve good privacy in the sense that the only thing that the server learns is something about the size of the database, and it knows which documents were returned, but only on encrypted form. Yet, from the practicality point of view, there is a lot of room for improvement on these works. They're mainly good for database that can reside on RAM. There are some improvements lately, including our work. So what is beyond the single keyword? Then the next natural thing is conjunctions. Give me all documents that have a sequence of keywords W1, W2 to some WN. Now, the solutions to this case are either brute force, what I call, which is basically take and do a single keyword search for every one of the keywords and return the intersection, or the ones that are more sophisticated than that are actually linear in the total number of documents in the database. And from these works, one main work that had follow-up is the one by Goldstad and Waters, which actually do minimal leakage in the sense that it only leaks the encrypted result set, but the complexity is linear in the number of documents in the database. Also has some other restrictions, like it works for single value, the attribute-based databases. It doesn't work for free text. So this is a very limited availability of solutions. So this brings us to our work, in which we actually do searchable symmetric encryption with support for Boolean queries. Essentially, we can answer any Boolean expression on keywords, such as I mentioned before, Alice, give me the messages with Alice as recipient, not sent by Bob, and containing at least 2 of these 3 words. And we can do it on relational databases. We can do it in free text. We can do it in any combination of these things. And it's efficient for a class of expressions of the form, give me anything that has keyword W1, and a Boolean expression, arbitrary Boolean expression on the rest of the keywords. In particular, this solves conjunctions on any number of terms and more complex queries like the example. And we can do any disjunction of these expressions. So it's a very, functionally, it's a very strong ability that the system has. Now, we also claim that it's highly scalable. And basically, the search complexity is proportional to the number of documents matching W1, which you would choose as the least frequent keywords in the conjunction or in the Boolean expression. And the pre-processing scales linearly with the database size. This allows us to deal with really huge databases. For example, we run experiments on synthetic census data of 10 terabytes, 100 million records, more than 100 billion index record keyword pairs, which from the point of view of size, you can think about having census data with more than 1,000 keywords per American household, or 400 keywords per American citizen. So it's a real-world example. By the way, these numbers are not the numbers that appear in the paper here. These numbers are for an improvement that we did later, but the protocol was not changed. So this is just better implementation. What is reported in the paper is about 30 times smaller than this, which is already big. We also have other examples, including this ClueWeb, which is a collection of websites, which include all of the English Wikipedia, meaning that you can search all Wikipedia, which is encrypted, and still ask any Boolean query and get the correct pages and in an encrypted form. And the query response time is basically competitive with plaintext queries, like MySQL queries on the plaintext database. What can we do about security here? Well, here is where the disclaimers start. In order to get that level of performance, you cannot do perfect security. I mean, there are some fundamental trade-offs between security and performance here. Many of these fundamental questions are still to be investigated, and this is one of the interesting open problems in this work. But anyway, the idea is that you are not going to give any plaintext data or any plaintext queries, yet you are giving what we call data access patterns. For example, if 2 queries return the same document, the server learns. It doesn't learn what the document is, but it knows that there is a document there. Repeated queries, for example, in our case, if you do 2 exactly same queries, we actually send the same tokens to the server. Now, this doesn't give you immediate information about plaintext, but of course, this allows you to do statistical inference, especially when you have side information. And to judge how much of that you can do is basically an application dependent. And there's another open question is really to understand better also what type of leakage and with types of database work better or worse. As I said, plaintext data or plaintext query are never revealed, but statistical inference is possible. Now, even though there is a disclaimer that we have to give up on perfect security in order to get performance, we shouldn't give up on formality. And really what we do is to have a formal model and a precise, provable leakage profiles that tells you, it gives you basically an upper bound on what you are actually leaking. I call all this story the challenge of being imperfect. We are used in crypto to give things that are always perfect, only with negligible probability things will go wrong. Actually, here we actually are giving some leakage, and we need to quantify it. So the security formalism follows the real ideal kind of definition. I will not go into details, but basically it means that anything that happens in the real game, in the real interaction between server and client, all of that can be simulated by a simulator that gets the information it gets is that leakage profile. Is this something that comes from previous works on single keyword search, and it's also very similar to leakage resilient computation that we heard the talk before this session. But the bottom line is that you really are claiming that the server learns nothing beyond what you define as your leakage, and if you have a proof of that. Let me give you just a fast overview of things that we are doing in the protocol. The protocol is quite involved technically, so I would need at least 10 minutes to go more into it, but let me do just two slides to give you the ideas. So first of all, we do Boolean expressions, but let's focus on conjunctions, W1 to Wn. Boolean queries actually are an easy extension of the protocol for conjunctions in this case. So we start by choosing what we call an S term for small. S is for small, basically is the least frequent term in the conjunction. And what we build, I mean, these at pre-computation, you store for every encrypted keyword a list of the documents that contains that keyword. All of that is encrypted. So you have the list from the encryption of W to the encryption of the indexes. This is not exactly encryptions. This is more PRFs, but this is the idea. So that's one element in the pre-processing. The other element is that we have an oracle that if it gets an encryption of an index and an encryption of a keyword, it will tell you if the keyword appears in the document with that index, okay, without revealing the index or the keyword. Now, we implement the oracle as a two-party computation between the client and server. Client enters its input, the encryption of W. Server takes the encryption of the int that is taken from this list. Server learns whether W is in int, but nothing else. So again, we have that oracle that goes from a pair enc int enc W to question, does keyword W appears in document int? We instantiate it as a two-party computation, which is non-interactive. This is very important for performance. And the idea is that the actual implementation uses a variant of the Diffie-Hellman oblivious PRF. For those that know that, interestingly, we don't use random oracles. So in that sense, it's not really the usual oblivious PRF, which does use random oracle. And the non-interactivity of the protocol uses a technique that you pre-compute some of the underlying protocol is interactive, but you de-interactive it by storing some of the message of the protocol during pre-processing, some blinding factors. The proof uses decisional Diffie-Hellman, no random oracles, which is surprising for something practical of this level, but actually that's kind of cheating because we do use random oracle in our implementation just because it reduces some communication in order to withstand adaptive attackers. For non-adaptive, we don't even need that. But the basic protocol really doesn't need the random oracle. OK, so as I said, we prove security of the protocol, but security in the sense of here is a leakage profile. I'll prove to you that we don't leak more than that. And that means that we will never reveal data, plaintext data, which is semantically secure. We don't use deterministic encryption. You don't see if values in the data repeated, things like that. Plaintext queries are not exposed. But this statistical leakage from access patterns and query patterns does lead on an application level to some information. This can always be mitigated by masking or padding, but that affects also the performance. For example, all these linear solutions in the number of documents, basically they pad all the runtimes or searches to the worst case. And you don't want to do that if you want to have something practical. So example of leakage that we provide is, for example, an upper bound on the size of the database or the index. We leak the number of terms in a conjunction. We leak the size of the set of documents satisfying or having the S term, the least frequent keyword W1. And there is a claim in the paper that this is unavoidable, but this is basically a conjecture. I mean, it's not a formal claim, it's a conjecture, and it's a very interesting question to research. We are getting some progress there, but still at this point it's a conjecture. And we also give the size of the intersection between W1 and each of WJ. So this is definitely not trivial leakage, okay? But on the other hand, it is certainly much less than if you were giving plaintext data or using the deterministic encryption. In subsequent and ongoing work, we have extended this to dynamic databases. The paper doesn't talk about what happens when the data changes. So we have now a paper doing it also for additions, deletions, and modifications of the information. We are working on supporting richer queries like range queries, substrings, wildcards. And we have a paper in CCS this year in November that shows how to extend this to more complex queries models. So for example, a multi-client model where you have the owner of the data puts the data in the cloud, but it will delegate access to the data to clients, but only on queries that the owner of the data authorizes. And yet another extension, which we called outsource symmetric peer, which is the same setting as before, but now the owner of the data is supposed to authorize queries under some policy that it has without actually learning the values of the query. So for example, you can have a hospital that outsources its database to the cloud. Now it has a policy saying this doctor can access these records, the insurance companies can access this information, and it gives tokens for these parties to do queries. But again, the hospital is not learning what the value of the query is. So if you're searching for someone with diabetes, then there is a policy saying you are allowed to search by sickness, but the hospital will not learn which sickness is that. And this is something which is important for regulations, liability. And to conclude, there are many challenges being brought by this type of work. So this is really a practical system. It has some leakage. Can we improve on that? What are the limits? And how do we evaluate leakage? This trade-off between security performance, everything is there to research what are the fundamental limits. Now, it is a work which is a result of really engineering and theory interaction. It's very important to keep everything simple. You cannot throw all the heavy weapons to the problem. And still, at the end, you need to have a proof. You know, I don't have to tell this too much to this audience. But none of these things without proof, they have no value, because if you just present the algorithm, what's the security, or what are you leaking or not leaking? So also complicating a proof is fine. Complicating a solution is not. That's something to take into consideration. I call this whole thing the challenge of being imperfect. And at the end of the paper, there is a list of open problems. So do you know where your data is? So with SSE, you know. The cloud cannot disclose your data, not even at gunpoint. Yeah. Thank you.
Okay, so thanks, Hugo. Are there any questions?
Supposing that your attacker has compromised some portion of the query, so they know the plain text of either the query or the results, does that give them any useful information for compromising other queries?
So that's a good question. The model that I went very fast through it, actually the model is that the attacker chooses the database. It knows the plain text. It chooses the queries adaptively. And still, it cannot learn anything beyond the leakage from seeing the interaction and the data at the server. So that is taken care of by the model.
Can your system be extended to queries which are sort of like circuits, in which the Boolean formula is computed on the fly, kind of, with temporary variables and things in the formula? Be a straight line program, say.
Like temporal. What would be an example?
Well, like if you were doing 10 out of 100, you might do that by a circuit that added up the counts.
So, I mean, you can do 10 of one
Right,
out of 100.
Yeah, but I'm imagining a more complex circuit that
So
has sub-expressions.
So we basically we can do everything.
Yeah.
But some of them will be linear in the number of documents. For efficiency, what we can do is anything that you can write as anything that has this keyword and anything else. Anything else is any circuit where the inputs are questions of the type of is the keyword in the document.
So let's actually make this the last question because we're running.
Is there any weakness due to data being kept in alphabetical or chronological order, or is it a pure database?
Well, the preprocessor can do whatever they want. They don't have to keep the data in any particular order. Usually, you would try not to do that. One question that is related to that: can you rank the data, return things that are some, like more important than others? You can, in principle, do that, but that already will mean a lot of leakage. So. And that kind of things is also part of the many open questions left by this work.
Okay, so let's thank Hugo again, and I guess he'll be available for more questions during lunch.